So good afternoon and welcome all to the JSGS public lecture on learning 6 impossible things before breakfast, a thought experiment on future debates over negative emissions technologies. It's presented by Dr. David Reiner, Deputy Director of the United Kingdom Carbon Capture and Storage Research Centre. The Johnson Shayama Graduate School of Public Policy is a provincial centre for advanced study and research in public policy and administration. The school is a product of a partnership between the University of Regina and the University of Saskatchewan based on the spirit of cooperation and collaboration, defining Saskatchewan. Saskatchewan is renowned for its innovation, and the Johnson Shayama Graduate School is yet another example of this. The combined expertise and resources of the two universities established the school and has created it as a source of respected policy advice and commentary. At this time, I would also like to acknowledge today's event is taking place on Treaty 4 and Treaty 6 land and the traditional homeland of the Métis. My name is Margot Hurlbert. I'm an associate professor here at Johnson Shayama, and I'll be your moderator today. And Dr. Jeremy Reiner in Saskatoon will moderate there. So today the school is pleased to welcome Dr. David Reiner, not to be confused with Jeremy Reiner, Dr. David Reiner. Dr. Reiner is a senior lecturer in technology policy at Cambridge Judge Business School at the University of Cambridge in the United Kingdom. His research interests include social and political acceptability of low-carbon technologies and climate change, science and technology policy. He's the assistant director of the Energy Policy Research Group, and he also sits on the steering committee of the International Energy Agency, the IEA, Greenhouse Gas Program Social Research Network, and a research associate for the Center of Energy and Environmental Policy Research and Carbon Capture Sequestration Technologies Program. Both of these are at the Massachusetts Institute of Technology, MIT. Dr. Reiner has many journal articles, publications, and research grants in the area of CCS, technology and climate policy. So we are thrilled to have Dr. David Reiner here today to talk about negative emissions technologies such as bioenergy and carbon capture and storage. Following the talk, we will have a Q&A, so please welcome me now please join with me in welcoming Dr. David Reiner.
Thank you, Margot. It's a pleasure to be here. It's always a pleasure to be back home in Canada. This is a visit that is partly pushing further our joint research project with Margot and Jeremy, that's looking at broader questions of the role of CCS in the energy system. And what I'm going to be talking about here, as I said to Margot, is kind of the first time I'm giving this talk, so bear with me. It might be a bit controversial in places, it might be a bit uncertain in places, and for that I beg your apology. Partly because this is kind of a new area. It's something that has been thought of for a while, but still is relatively new. So maybe, I'm not sure I can ask a show of hands in Saskatoon, but just to give a sense of at least people in the room here in Regina, how many people will have heard of negative emissions technologies? Okay, that's pretty good. More than half. That's probably better than most places I would go to. So I'll try to give a brief introduction and then pose some challenges, questions about the future of these negative emissions technologies. So let's see. So the first thing to say about NETs, or negative emission technologies, is that unlike what we consider to be conventional mitigation, nuclear power, renewables, CCS, with fossil fuels, negative emissions technologies actually allow for a net flux of carbon out of the atmosphere into long-term storage. So rather than just reducing emissions, we can somehow get below zero. This is sometimes hard to get our heads around, and a lot of this has to do with particularly critically the way in which the fuels we're using are being used sustainably. So it's important because unlike anything else that we have in our arsenal, they actually will allow us to address emissions that are already in the atmosphere. Yeah, it's sort of a funny idea that emissions that are already up there could somehow be addressed by what we do today or tomorrow or in a few years. And there's a wide suite of these negative emission technologies, which for better or for worse, and we can come back to that later maybe, in the initial definitions of geoengineering, of large-scale geoengineering of the planet, originally as defined by the US National Academy of Sciences and also the Royal Society in the UK, they list these negative emission technologies as part of that suite of geoengineering. The leading, arguably, net is bioenergy plus CCS. So you grow your biocrops sustainably, so that they're essentially a sort of net zero in terms of their impacts on the climate system, and then you take that CO2 that's been generated by burning this bioenergy, and you store it long term, and so that would give you a net negative. There's a whole range of other technologies, enhanced weathering, the idea of we could have cements, for example, that as you build a home over the course of its lifetime will absorb CO2 from its surrounding. Large-scale ocean liming, afforestation, not just planting a tree or two, but massive programs of afforestation, biochar, direct air capture. Some of these are largely at the experimental stage or kind of the thought experiment stage. But so there's a wide range of these sorts of negative technologies. And the retort or the question or the concern is that many of these things are just, well, frankly, impossible. So the first impossibility that I'll come up with is that nets are really just a figment of modeling. So we you might be able to do a little bit here or there, but fundamentally we're talking about a technology that isn't being driven by commercial drivers, isn't being driven by the state of their development, but they're being driven by models, these economic models that say that without these kind of magic wand of negative emission technologies, we won't be able to reach our targets, our global temperature targets. And I'll work through that a little bit. And I think there is some truth to that. But it's also true that there are some grounds to believe that we can make progress on these technologies. I think there are important analogies, for good or for bad, with more developed existing technologies such as carbon capture and storage with fossil fuels or biofuels. And I think the real question is, how desperate are we, and we'll keep coming back to this, how desperate are we to meet our, say, 2-degree target for global temperatures? Are we willing, or for example, those lobbying for meeting that target, say in the environmental community, willing to tolerate some of these negative emissions technologies that may be quite problematic? And I think it's also important to say that these models, these integrated assessment models that have helped give rise to the interest in these nets, don't make any judgment calls on their feasibility. They're just saying, well, essentially, if we want to get from here to there meaning say 2 degrees or even lower, then it's hard to figure out how to get there without these technologies. So just to make sure everybody is on the same page, if we would like to eventually stabilize atmospheric concentrations, we will need to stop increasing sort of the global global emissions. The history for the last century and a half, but especially even over the last 40 years, shows that global emissions have increased dramatically, more than doubling since 1975. Over the last decade and a half, most of that emissions growth has been driven largely by Chinese emissions. It's also important to say that if we really wanted to get dramatic reductions in emissions, it needs to come not just from the power sector, which is kind of the easiest place to target, but we're going to need to see, in the UK, for example, in Europe, we've committed to an 80% emissions reduction target. Completely decarbonizing the power sector will get us, 30%. To get to 80%, we need to start getting emissions out of industrial processes, so like the chemicals sector, cement and so on, but also from heat, so natural gas and heat. And so how we actually imagine this will need to really push hard. And again, to date, we're having enough trouble just decarbonizing, just reducing emissions from the power sector. So the IPCC, every few years does a big report. Its last report that came out in 2014, its fifth assessment report, showed that we would need quite a dramatic upscaling of both low and zero carbon energy relative to their baseline in 2010. So we're talking about doubling, tripling, that sort of kind of hard to imagine, but a very dramatic increase in low carbon energy. And again, this would be across the power system, where we'll have to move to almost 100% low carbon fuels, but also increasingly in our liquid fuel supply, so that all of these lovely automobiles and SUVs that we see out here in the parking lots will need to shift increasingly towards lower carbon fuels, whether that's biofuels or hydrogen or electric vehicles. The types of investments that we're talking about are really quite dramatic. The sort of numbers are in the sort of hundreds of billions of dollars per year globally. So very large investments that would be required. Just to give you some sense of comparison, our current investments, say in renewables, is in that green star, 250 billion or so. This is the additional increase, sort of roughly doubling what we're currently investing in renewables. On something like energy efficiency, we'd need to much more dramatically increase by many-fold the amount of investment that we'd see to get to these, to get to be on target. And to just give you a sense of ballpark, currently global fossil fuel investment in 2013, those numbers are probably down in 2016, but are on the order of 1.1 trillion. So these are large numbers. Again, starts to get into some of these impossibilities that we can talk about. But so why do we keep coming back to negative emissions? It has been driven by what was first enshrined in Copenhagen and then in the Paris Agreement, a global target of a 2-degree limit. To get there, and those are the blue curves on the kind of bottom right. What we're saying is by the last quarter of this century, we will need to go into this territory of net negative emissions. So, either we're going to miss or likely miss, because again, it's these are all probabilities. There's no way of doing this in a deterministic way, and that's why you have this range of 0.9 to 2.3 or 1.7 to 3.2. But under these broad range of concentration pathways that the IPCC talks about, if we really wanted a significant chance, better than 50% chance of meeting this 2-degree target, we're going to need to get somehow these net negative emissions. Again, a little bit hard to get your head around in some ways. And we'll talk about ways in which this might happen and some of the problems that might result from these emissions trajectories. So the first thing to say is that the main kind of the fastest runner amongst these negative emissions technologies are what we call Becks, right? So Margot had to spend all this time over all these long words and my various affiliations where we just use acronyms. So the reality is we end up using a lot of acronyms because saying bioenergy with carbon capture and storage is a bit of a mouthful, so we say Becks a lot. And so Becks is seen as the leading opportunity for these negative emissions technologies. But then that raises the question of, well, for Becks to work, that's kind of a subset or we're a lot less far along on Becks than we are on just regular fossil-fired CCS. And if we look at the history of CCS, we see, a history of some, a number of failed efforts and some limited success. Again, if negative emissions technologies are being driven by a logic that the models tell us the only way to meet our ambitious targets are to invoke these sort of magical, perfect technologies, CCS to some extent also has had that rationale driving its driving enthusiasm for moving forward with CCS. If you compare CCS across a number of other technologies, and so what the IPCC in this case did was to say, well, let's say nuclear was unavailable. What impact would having nuclear not be available? And you see that, well, that slightly increases our costs, but we actually are in pretty good shape of meeting our target of, say, 550 ppm, 3 degrees, if we didn't have any nuclear. And we just phased it out everywhere. Even if we significantly limited solar and wind, so we said nuclear is back on the table, but there are lots of problems getting solar and wind going, that would, again, increase costs 10, 20, 30, 40%, but not all that significantly. If bioenergy is limited, that drives costs up more like 60%. But if we didn't have CCS, then that more than doubles the global costs of meeting our target. So there's a different way of showing it, but essentially, the more ambitious we are, there's always been a very strong rationale for CCS being driven that way. It's also worth saying that I mentioned these integrated assessment models. These models can't actually even solve or can't get you solutions in many cases if you don't allow for CCS. So again, that doesn't mean CCS will happen, but it does mean that our best understanding of the economics of reducing emissions means that either we're going to have to pay a lot more, or we won't be able to meet our targets at all if we take some of these things off the table. Now the challenge, of course, is that over time we would need a very dramatic increase in again, there's been a lot more work on CCS than these nets, but what the IEA showed in 2009 was by essentially today in 2020 we would need something like 50 to 100 CCS plants by 2025, which is only 8 years away and essentially around the corner in the context of building large-scale infrastructure. You're talking about over 300 CCS plants that would be needed according to this kind of rollout scenario. a few years go by, the IEA says, we're having some problems. We haven't noticed dozens of CCS plants being built. So they had to kind of scale down kind of the initial projections. But fundamentally, we're still driven by the same envelope. We're still driven by the same goals of meeting these ambitious targets over the next few decades. And so therefore, the numbers don't really change, even though the facts on the ground are making it harder. I kind of show this in a paper I did last year, showing that in 1998 there's virtually nothing. By the time the paper was published in 2015, we have a few ticks, a few positive things going on, and also a few X's. I didn't show the larger number of projects that were canceled, but a fair bit of progress. In my current country of the UK, we've had some issues with CCS, big X, in terms of the second UK competition being canceled. In other places, notably at Petronova in the U.S., we've seen some significant progress. There are some egregious examples of problems. Kemper County, which was in that climate-friendly place of Mississippi, was being built largely to supply CO2 to the oil fields in the region. Was kind of has spent a lot of effort trying to push back on its critics, but has proven to be a bit of a white elephant. It's now 4 years after its deadline and several billions over budget, and again is often used as a bit of a cudgel to beat on CCS. But by the same token, there are some significant progress. I mentioned Petronova in Texas. Sleipner just had celebrated its 20th year of storing 1 million tons a year of CO2, and as we all know, locally there's a Boundary Dam. It's important, I think, to mention though that if you think of these three projects, what got Petronova off the ground was U.S. stimulus spending. So in 2009, partly as a way of getting injecting lots of money into a very fragile economy, billions were pumped around across a number of infrastructure projects, and some of the projects in the U.S. that are going now, whether it's in CCS or a number of other areas, are being driven by that kind of old, now 8-year-old spending. And there's questions of renewal. Sleipner was driven by amongst other things, a very high tax on CO2 that the Norwegian government had imposed on Statoil, and so they responded quite rationally. And I think it is important that the particular circumstances that led to the success of Boundary Dam included both the economics, but also, I think, importantly, the politics, where there was kind of a strong political leadership on the issue. So again, every analysis will gives us sort of similar answers. This is in the UK. Our Committee on Climate Change talks about how we'll be needing these technologies. But in reality, it's proven to be quite difficult. In spite of a decade of UK championing of the technology, what we've seen at the political level is a failure. And I think some of the challenges that Lord Oxborough describes CCS as an orphan technology, and in many ways that's part of the problem. Unlike nuclear or even onshore wind, there aren't really very many strong opponents, but you also, by the same token, don't have a huge number of strong proponents who will lobby actively for the technology. I think Again, in the UK, I think we've had a problem where there has been less compelling policy logic. You might have, for example, been able to focus on, I don't know, saving our dying industrial clusters by trying to address industrial CCS. We haven't really found at least a compelling policy logic. I think part of the problem that CCS has faced, and I think that many of the nets will face as well, is this just seen as some sort of get out of jail free card? In the case of the US, it was the Bush administration that championed CCS as an alternative to taking other action on climate change, or any other action on climate change, and also from withdrawing from the Kyoto Protocol. I think an important big problem for carbon capture is that it is virtually the only technology that is entirely dependent on climate policy. So nuclear power, wind power existed long before we started worrying very much about climate change, whereas CCS is much more of a bellwether for our attitudes on climate change. And as an example, 2009 led to this brief injection of funds, as I mentioned, in terms of stimulus spending, but also was a bit of a downturn in terms of kind of the financial situation that we still have in Europe, kind of the failure of the Copenhagen process, our European the European emissions permit price, which had been meant to fund CCS projects in Europe, for example, were linked to that funding, and ultimately we had been expecting to get several billion euros of funding for CCS and got a third of that because the carbon price in Europe was considerably lower than we had expected. Because all your Kyoto targets were easier, it reduced our ambition and made it harder for us to say, well, why should we be adopting these more ambitious projects? I think the other challenge, and I mentioned Kemper County earlier, is that the nature of R&D, even though they're large-scale projects, the nature of research and development means that we will have failures. Okay, it's not so bad when you have a portfolio of $1 billion and you're giving it to 100 different projects of 10 million, and you're happy that 90% of them fail. It's a lot harder when they're billion-pound projects. And the problem with CCS is that it's much lumpier. They come in much bigger chunks, and that means that these are much more visible failures. And then, as I said, I think the biggest challenge, and I think there's some good examples, but we've gone through a number of iterations in terms of what are good narratives, effective or compelling narratives, and it's not clear any of them have really stuck. The idea of saving coal, which has now come back, I think, with maybe the new Trump administration, the potential for decarbonizing China. Our first UK CCS competition explicitly prevented gas plants from becoming involved because the goal was we were meant to be a light onto China. So China was meant to be looking at the UK for post-combustion coal plants, and we were meant to be inspiring them. That kind of very, I don't know, hubris is probably the right word, but maybe not surprising for an imperial power, a former imperial power. So I think there are questions in terms of what the model is. The idea that it's dispatchable, that CCS allows for flexible power in a way that nuclear power or renewables do not, is amongst my engineering friends very appealing. Doesn't maybe have as much of a saliency in the wider public. So that's one of the questions: how to make this more appealing. And I think nets just bring these issues up even more to the fore. Having said all that, mentioned all the problems, every study that comes along says, we just can't get there without very significant upscaling of CCS. Glenn Peters, who does really well with kind of some of these figures, has tried to show, again, over the next 25 years, 20 years even, what sort of future kind of pathways you need to get to 2 degrees. So you need very significant increases in solar and wind from where we are today, but we're more or less, I don't know, arguably on course. But for CCS, we're going from kind of a black flat line to kind of a very sharp increase that would be needed. I think another important change, and I think that's where nets come in maybe as kind of a new way of thinking about it, is a decade ago, even less than a decade ago, when we were focusing on CCS, it focused almost exclusively on power. So in the EU, we have a zero emissions power plant kind of focus. And that has now slowly begun to expand beyond electricity to include heat, industry, and transport, as I said earlier. Another impossibility, another thing that you will often hear, with regard to CCS or renewables or many things, is just this will be too expensive, far too expensive. And I think the rebuttal is, but we do lots of things, and many of these things we do as a society are very expensive. There are some white elephants in there, but there are also some very positive things that we do. They may not all be inefficient. They might not be all the most efficient use of our funds, but often you have very strong political appeal to these, and I kind of will show you a few, and you can guess, or you can have your own take on which you think are desirable or undesirable kind of ways of spending billions of dollars or pounds or euros. But often they're rooted in some sort of deep-seated desire to go into space or discover new things, or things that we deem as essential. So how much do we spend in terms of stabilizing the global financial system post 2007-8? I mean, the numbers are clearly in the trillions, I think. For energy, often the reason why we have these massive projects is either a belief that there will be significant learning over time, which I think is important, and it's not always clear that the learning materializes, or that we expect a certain type of world. And Mike and I were just talking about this yesterday, I think. But sometimes there's this view that we're going to have a high oil price world for many years to come, or a low oil price world for many years to come. And it's very difficult to get out of that mode, and we initiate projects of infrastructure which will last for decades. So, just to give you a sense of things we have done or are talking about doing, International Space Station, it's been up there for almost 2 decades, cost roughly ballpark $150 billion. We're talking about, again, reviving a talk to a mission to Mars, depending upon who you talk to, somewhere in the range of $100 billion to $1 trillion. The F-35 Joint Strike Fighter, which even many defense hawks find to be sort of not a very good plane, still is going forward. The U.S. Is producing roughly 2,500 at a cost of about 1.3 trillion. At a more prosaic level, we built in the UK what had been the largest kind of offshore wind turbine farm, 175 turbines at a cost of $1.8 billion. Again, for 600 megawatts, you could have built a gas plant and it would have been considerably less than $1.8 billion. Again, not too far away, in Beulah, North Dakota, you have the Great Plains Synfuel plant, again, motivated at the time by a concern over energy independence, roughly, in today's dollars, $4.9 billion. Kashagan, which was often a sort of unfortunate name because people often refer to it as Kash Algan, in Kazakhstan, rose from sort of a $10 billion estimate to over $50 billion. It just started at the end of last year. It began in a high oil price world. It's now operating, but of course the fact that it's now operating, and it's a very significant field, has actually helped collapse the oil price over the last a few months. They've had technical problems, but they also have questions as to why they built such an expensive plant into a world of not $100 a barrel, but closer to $40 a barrel. So my fourth impossibility, just to whiz through the last few, is that these negative emissions technologies are not just, they might not be only impossible, but if they are possible, they might be quite undesirable. The term of moral hazard is used in insurance, the idea that people behave more recklessly if they think they are protected. Right. So if you are, people are concerned that you, if you are have a seatbelt, you'll drive more recklessly. If you're insured, you'll behave more recklessly. Those who are opposed to universal health care in the U.S. sometimes make this argument that it's undesirable to have this sort of national health insurance because of kind of the behavioral implications that will result. And I think in the case of these nets, the concern is that this will discourage society from taking action. And the question, I think, is not so much that we're going to have many gigawatts of these nets tomorrow or the next year or the next decade, but the question is whether this is a kind of a plausible plan B or whether this is something that we really shouldn't be focusing on, and we should focus on lots of other things beforehand. And in addition to these negative emissions technologies I mentioned, there are also these so-called other ways of affecting the climate, such as ideas of taking, say, a U.S. or a Chinese destroyer, sailing it out into the middle of the Pacific and firing sulfate particles into the lower atmosphere, which will then act to cool the globe. Large-scale ocean liming would also maybe have similar effects. The challenge here, of course, is that we're replacing our current global planetary experiment, which is pouring gigatons and gigatons of CO2 into the atmosphere, with yet another much less well understood experiment or set of experiments. And this is just different ways of showing it, but most of these models talk about really very significant negative emissions. So we're not talking about building 5 boundary dams with bioenergy. We're talking about 20 gigatons a year of these negative emissions technologies. So the scale that we're talking about really is quite dramatic. And when we're talking about that sort of scale, we're also talking about essentially implications for food crops, and I'll get into some of those things in a minute. But the numbers are really quite dramatic. Our current trajectory is still ever upward. So the shaded area in gray is kind of our current emission pledges. It kind of takes a little bit of the edge off, reduces our trajectory a little bit below where we would be going otherwise, but still there's a very long way to go without significant net emissions. Kevin Anderson, who's at Manchester, and Glenn Peters, who's at Cicero in Norway, talks about this, and they recently wrote an article at the end of last year kind of challenging these, as they call Dr. Strangelove technologies, because their point is that the beguiling appeal of relying on these nets will delay the need for stringent and politically challenging policies today. So they have this model, kind of mental model, that nets are really dangerous because otherwise we would be taking much more substantial action, but this allows us to pass the buck for reducing carbon onto future generations. I think my retort to this is that to believe that's true, that believes somehow that we wave our wand and nets disappear, and then all of a sudden we'll see all this dramatic and very serious effort to reduce emissions otherwise. I think it's just, I think that I find probably the hardest to believe. I think, I think it's quite likely that given political and social inertia, given the inevitable challenge of rolling out these technologies at scale, whether that's battery electric vehicles or CCS at a larger scale, whatever it is, I think it's hard to imagine that we won't overshoot, that we won't be sailing well through the 2-degree target. The question is, how do we respond to that? Do we say, okay, let's stay within our kind of set of acceptable technologies, and we'll have debates over those, or do we try and do something much more dramatic and start effectively trying to suck CO2 out of the atmosphere? Is this a plan B that we want to think about seriously, or is this plan Z that we don't worry about and we try and do everything else? I'm not expecting you to read that, other than to say, the Economist and many others question some of these models. So I think there's first questions as to the validity of some of these models, whether they are imaginable. And my colleague David Victor, who's now at UCSD, and Charlie Kennel, who's former head of Scripps Oceanographic Institute, talk about the challenge, the misplaced problem of this 2-degree goal in the first place, that it's wrong-headed, and it allows us to pretend that we're doing things because they're kind of long distance. So the UK can set an 80% target for 2050 from our previous target of 60%. So we had a 60% target, which we weren't on track for. But since it's 2050, we can say it's 80%, and there's no consequences. So their point about 2 degrees is because it's so far away, it allows everybody to just kind of wave their hands and say they're doing something. So I think that's that's one of the questions. Let me try and go back. My last two impossibilities. I didn't go away too quickly. That nets actually can potentially, I showed that big amount of money that we need to spend on energy efficiency. There's a sense in which a world that is where nets are common will actually be turn everything on its head. We no longer want to save energy. We no longer want to be energy efficient, because the less energy efficient you are, the more carbon you're pulling out of the atmosphere, right? So in this bizarro world, a policymaker will think of measures that will encourage energy use, right? We should be having these lights on in the middle of the day instead of turning them off, because that will reduce our emissions faster. We want less efficient plants because that will yield higher net negative production. An architect will say, oh, well, if we're having cement that is sucking CO2 out of the atmosphere, bigger houses are better. And what does that leave kind of the world of, an environmentalist in net world to do? Do they say, consume, consume, consume? Slightly hard to imagine, right? It very much goes against the ethos, many of our beliefs, many of the ways we believe things should do better. But it does start to at least push and challenge some of these views. And then finally, I can't spend a huge amount of time on it, but I think one of the critical questions about all this, whether that's on afforestation or on the sustainability of the bioenergy that's being used in Becks, is that fundamentally anytime you're challenging or competing with food crops, you run into a dead end. So China had a very ambitious biofuels program. 2008 or so comes along. Food prices are going, rising ever higher. The Chinese government essentially brings its biofuels program to a halt because it's worried about, its food independence and self-sufficiency. So, governments don't respond well to this challenge. And I think the sort of numbers that you'll need if you are talking about those kind of 20 gigatons of Becks, right? That's very big numbers. We'd be talking about using up almost all of the arable land to be able to grow the food crops, what had been food crops, and to use them for fuel. And how do you feed a world population where increasingly people are getting wealthier and demanding more, better diets, more meat in their diets, and so on. And so, that can be potentially a complete showstopper. By the same token, we do have, a strong track record in terms of agricultural productivity. The Green Revolution doubled crop yields between 1965 and 2000. We have, obviously here, many other countries, many other research institutes, lots of work going on trying to understand how to grow fuel crops on marginal land. So you wouldn't be competing with arable land. You'd be going into areas that aren't otherwise appropriate for food crops, and also the potential significant biotechnology applications. So do you get into this debate over, food or fuel? Do you wind up having to take this debate into a very contentious area, or can you kind of try and solve this problem through technology, as again we've successfully done in the 1960s. Again, if you would have told somebody in India that you would be able to feed its current population of over 1 billion with given agricultural productivity and yields in the 1960s, there was a lot of justifiable alarm over that, and we have been able to rise to the challenge. There are many ways of describing what the next steps are, but one sort of positive, very timely things to report is, at least in the UK, where we have a new CCS research center, which we've just launched last week. Part of its mandate is specifically to look at Becks, and we have a lot of work that's going on under Becks. And also the UK Research Councils today, as of a couple of hours ago officially, have announced a new major research program on greenhouse gas removal technology. So just to show you, just again, some sense of what we're trying to do, bringing together my friends who are working on capture, those who are working on systems and systems integration, and those who are working on policy like myself. And we have, kind of half of our work packages, half of our work program will be contributing to work that we're doing on Becks. I'm also part of one of these 4 consortia. The last one here, the last one on comparative assessment and region-specific optimization, but a lot of work at the more basic, more fundamental level, such as divalent cations to sequester carbon on land and sea, to understanding soil productivity, soil research, a number of other areas, including from a policy point of view, this question of what are the impacts of these nets or these greenhouse gas removal technologies on deterring mitigation. So will we really see that? And so that's some of the work